Okay, welcome everybody. This is a run through of the Combined Science Chemistry Paper 2 mock. Get your green pens out and get ready to mark your work and improve it. The paper starts on question 2 and it says a chlorine atom contains 17 electrons, 18 neutrons and 17 protons. State the mass number of this chlorine atom. The problem there is that if you look up the relative atomic mass of chlorine on your periodic table, it gives you a value of 35.5. Well, that's not the mass of this particular atom. The mass of this particular atom comes from its 18 neutrons and 17 protons. And if you add 18 and 17 together, you get the mass, because the mass comes from neutrons and protons only, and that number is 35. So the answer in here is 35. Give the electronic configuration of this chlorine atom. Well, it contains 17 electrons. The rule for the electrons is 2, 8, 8. And if you make 17, you've got 2, 8, and it's got 7 electrons in its outer shell. I think the problem there is knowing what the word electronic configuration means. That means give the number of electrons in the 2, 8, 8 format. The next one, part B, describe what you would see if damp blue litmus paper is placed into chlorine gas. Well, normally with gas tests you get 2 marks, 1 mark for the test and 1 mark for the result. But with this one, it tells you what the test is. You're going to add damp blue litmus paper, and 2 things happen when you do that. First of all, the litmus paper turns red, and then is bleached. And bleached means that it turns colourless, or it turns white. So you need to say 2 things. First of all, the damp blue litmus paper turns red, and then it's bleached or turns colourless, and you get 2 marks for that. Moving on to part C, it says chlorine exists as a diatomic molecule. In a molecule, 2 chlorine atoms are joined by a covalent bond. Describe what is meant by a covalent bond. Now, there are lots of good ideas here about covalent bonding. A covalent bond is a strong bond between non-metals, but unfortunately those don't get you the mark. A covalent bond is a shared pair of electrons, and that's all you need to know, and that's the 2 marks. And many people put down that it's shared electrons, but you have to say that it's a shared pair of electrons. So a shared pair of electrons. And literally that is the definition, and you got 1 mark for saying shared and 1 mark for the pair of electrons, giving you your total of 2 marks. Part 2 says explain why chlorine is a gas rather than a liquid at room temperature. Well, anything that is a gas has a low boiling point, so chlorine has a low boiling point. So in other words, at room temperature it's already boiled, and it's got a low boiling point because of its structure. And the structure of chlorine consists of molecules. Now, chlorine goes around in pairs. It's Cl2. Now, what that means is that the structure of chlorine consists of chlorine atoms that are held together by strong covalent bonds to form a chlorine molecule. Now, when chlorine boils, it's not the covalent bonds that break. The molecules are held together by weak intermolecular forces. And it's the weak intermolecular forces that break when the chlorine boils. So chlorine has a low boiling point because molecules are held together by weak intermolecular forces which are easily overcome by heat energy. Part D says, when the gas hydrogen chloride HCl is dissolved in water, a solution forms. Blue litmus paper dipped in the solution turns red. State why the litmus paper turns red. Well, you'd have got the mark if you just put the solution is acidic, and it's acidic because it contains hydrogen ions, H plus ions, and what actually happens is your HCl splits up into H plus and Cl minus ions when it's in solution, and therefore it's acidic. Question number 3 says, lithium, sodium and potassium are reactive metals in group 1 of the periodic table. Sodium metal tarnishes in air to form a layer of sodium oxide on its surface. 0.92 grams of sodium combined with 0.32 grams of oxygen in this oxide. Calculate the empirical formula of sodium oxide. Now, you should be able to write down a formula for sodium oxide. Sodium is 1 plus, and oxygen is 2 minus, so you'd expect the formula for sodium oxide to be Na2O, but you've got to prove that by showing your working, and the way that you're going to do this is you're going to write down the two elements, Na and O. You're going to write down the grams that you've got of each. Sodium 0.92, oxygen 0.32, and then you're going to divide the grams by the rams, the relative atomic mass. Okay, that's not the formula mass for oxygen, so it's not 32, it's 16, so it's Na 23, oxygen 16. Divide the grams by the rams and you get two numbers, 0.04, 0.02. Now you find the simplest whole number ratio. Well, this side is twice as much as this side, so I've got Na2O1, so which is Na2O. Well, that agrees with what I thought it was going to be, so that seems a pretty reasonable answer, Na2O, and that's a very easy way to get yourself 3 marks. The second part of the question, sodium reacts with water to form sodium hydroxide solution and hydrogen. Complete the balancing of the equation for this reaction and add state symbols for each substance. Well, I need to end up with 2 hydrogens, 3 hydrogens on that side. I've got 1, 2, 4 hydrogens there. I'm going to need 2 NaOH because I've got 2 oxygens on the left hand side. I need 2 oxygens on the right hand side. That gives me a total of 4 hydrogens on the right hand side. I've got 4 hydrogens on the right hand side, but I need 2 sodiums. So 2 marks out of the 3 were for putting the 2 balancing numbers, 2 and 2, and then the state symbols. Sodium is a solid, water is a liquid, it's not AQ, it's a L for liquid, NaOH is AQ, and hydrogen is gas, and that gets you a simple 3 marks. In an experiment, equal side pieces of lithium, sodium, potassium are added to separate samples of water. A flame is produced only with potassium because potassium, the answer is C, the most reactive metal. And I think that was quite an easy mark. Part D says explain in terms of the electronic configurations that increase in reactivity from lithium to sodium to potassium. Well, lithium, sodium, potassium is going down the group. So as you go down the group, the atoms get bigger. Now you need to know that group 1 metals react by losing their outer shell electron. Sodium has got 1 electron in its outer shell and it reacts to give the sodium ion Na plus an electron. It loses its outer shell electron. Now as the atoms get bigger, the electron is further from the nucleus and is easier to lose. And the reason for that is that that electron is held in to the atom because it's attracted to the positive nucleus, and therefore the bigger the atom, the further the electron is from the positive nucleus and the easier it is to lose. So as you go down the group, the atoms get bigger, the electron is further from the nucleus and easier to lose, meaning the atoms are more reactive, and that will get you a good 2 marks. Question number 4 is about crude oil. Crude oil is a complex mixture of substances. Crude oil can be separated into useful fractions by fractional distillation. Figure 3 shows a fractional distillation column and the fractions produced when a sample of crude oil is distilled. The properties of these fractions vary from the top of the column to the bottom of the column. Which of the following is the trend in the property of the fractions attained from the top of the column to those obtained from the bottom? Now, things that come off at the top are small molecules, which are good fuels, and so they contain a small number of carbon atoms. So the average number of carbon atoms in the molecule present decreases while it doesn't. It increases as you go down. The ease of ignition increases while it doesn't. It decreases as you go down. The boiling points decrease while they don't. They increase as you go down. So the answer's got to be D. The viscosities increase. The viscosity is how thick the substances are, and yes, bitumen, which is used for tarmac, is a very thick substance, so they get thicker as you go down the column. Part B, most of the substances in crude oil are alkanes. Which of the following is the general formula of an alkane? Well, in an alkane you have carbons, and then for every carbon you have 2 hydrogens. So there's my 2 hydrogens for every carbon, and you've also got an extra 2 because you've got 1 at the start and you've got 1 at the end. So that means every carbon has twice as many hydrogens plus 2. So for N carbons, I've got 2N hydrogens plus 2. So the answer is D, CnH2n plus 2. Part 2 is an easy 2 marks. It says explain why alkanes are described as hydrocarbons, and the answer is they contain hydrogen and carbon atoms, and then the key word only. They only contain hydrogen and carbon, and that's what makes them a hydrocarbon. Part C says figure 4 shows a graph of the boiling points of some alkanes against the number of carbon atoms in one molecule of each alkane. And it says, explain the pattern shown by this graph. Now the key word there is explain the pattern, and if you're asked to explain a graph, you have to first of all describe it for 1 mark and then account for it for the 2nd mark. So the pattern is the bigger the number of carbon atoms, the higher the boiling point. So you got 1 mark for saying that. The greater the number of carbon atoms, the higher the boiling point. That was for 1 mark. And then the 2nd mark was for accounting for it. And this was quite a tricky mark because you need to know, again, that hydrocarbons form simple molecular structures. So if I had a hydrocarbon like that, it would form a molecule, and that molecule is attracted to another molecule with, yes, you've guessed it, intermolecular forces. And the key thing is that the bigger the molecule, the bigger the intermolecular forces, so therefore the higher the boiling point. So the higher the boiling point, because bigger molecules have bigger intermolecular forces, which need more heat to overcome. And that's a really good answer to make sure that you've got your 2 marks. Part D says 1 crude oil is separated into fractions. The amount of each fraction obtained rarely matches the demand for that fraction. Figure 5 shows the relative amount of 6 fractions obtained from crude oil and the relative demand for each of these fractions. It then says cracking is used to match the relative amount of a fraction of crude oil to the demand for that fraction. Use the information in figure 5 to give the name of the fraction that is most likely to be cracked. Well, cracking turns long chain hydrocarbons into short chain hydrocarbons, so I'm only going to crack these ones over this side because these are my long chain hydrocarbons, and one of these, the supply is huge, and that's fuel oil. So fuel oil has got a big supply. I could crack it and turn it into shorter chain hydrocarbons, something like these ones, which would be are in high demand. So the answer is fuel oil, because that's a long chain hydrocarbon that is in high supply. Now, part 2 was particularly badly answered, and it says, in a cracking reaction, reactants are heated to form products. The reaction is endothermic. On the axis provided, draw the reaction profile. Okay, reaction profile of this reaction. Well, a reaction profile is an energy profile diagram. You've got the energy up the side, you've got the progress of the reaction along the bottom. Now, you're in an endothermic reaction, heat is taken in from the surroundings, so the energy of your reaction increases. So I need to draw the energy of my reactants, and then I need to draw the energy of my products at higher energy. Now that is the difference between the two is the energy taken in during the reaction. But the key thing here is that I also have to draw the activation energy. So it doesn't go straight up, it goes to a higher energy level state first of all and then comes back down. And so the barrier that I have to overcome for the reaction to happen is the activation energy. And the activation energy is from the bottom to the top up here. And that is the EA, the activation energy. Now, you needed the activation energy, the reactants lower than the products. If you drew the correct diagram for an exothermic reaction and you labelled everything correctly, you actually got 2 out of the 3 marks. But that was the diagram that you needed for 3 marks. Part 3 was really quite straightforward and there's no information that you needed. You just need to be able to do a bit of maths. Dodecane C12H26 can be cracked to form useful products. Complete the equation for the cracking of dodecane by filling in the formula of the single molecule. So it's only one molecule, that's the key bit of information. Single molecule needed to balance the equation. Well, on the left hand side I've got 12 carbons, and on the right hand side I've got 3 lots of 2 carbons, so that's 6 carbons. So I'm going to have a molecule that's got 6 carbons, C6, and on the left hand side I've got 26 hydrogens and I've got 3 lots of 4, so I've got 12. 26 minus 12 gives me 14, so I've got C6H14. Now that is the formula of a short chain alkane, and just to check I've gone from a long chain alkane to a short chain alkane and an alkene, so that fits in because this is C6 CnH2n plus 2 and that works for that. Question 5 is a halogen displacement reaction, and it says, first of all, describe what is seen when chlorine water is added to potassium bromide solution and the mixture is shaken. Well, first of all, you need to establish chlorine water is a very pale green colour. Potassium bromide is colourless. And you need to decide what happens when the reaction takes place. Well, it's a halogen displacement reaction, and chlorine is more reactive than bromine, and therefore chlorine is going to steal the potassium from potassium bromide to make potassium chloride. Well, potassium chloride is also colourless, but it kicks out bromine, and bromine is orange brown colour. Now, if you're confused by the colour of halogens, you need to remember that the halogens are only coloured. I'm going to write this down actually. The halogens are only coloured when they go around in pairs. So Cl2, Br2, I2. This is green, brown, orange and purple. But they're not coloured when they're salts. So sodium chloride, NaCl(Kbr), salts are colourless. And therefore what you're going to get is you're going to get changing colour from colourless. So the potassium bromide, the Kbr solution turns from colourless to orange stroke brown. Now that question in a way is made easier if you go down to part B, because it actually gives you an equation for the reaction that's happening in part A. It says chlorine reacts with potassium bromide, well that's what you were given up there, to form potassium chloride and bromine. So it actually tells you what's made and gives you a symbol equation for it. In this reaction, chlorine forms chloride ions. So chlorine changes to potassium chloride. In this reaction, chlorine has been reduced. Explain using the equation how you know that chlorine has been reduced. Well, Cl2 goes to 2Cl minus. Now what happens there is that chlorine, which has 7 electrons, turns into chloride, which has a full outer shell. So it's actually gained 2 electrons. So 2 electrons plus. Now, reduction is gaining electrons, Rig. Reduction is gain. So the answer is, how do I know that chlorine has been reduced? The chlorine atoms have gained electrons to give chloride ions, and that would get you your 2 marks. The next part says write a half equation for the formation of bromine from bromide ions. Well, we've got to get that round the right way. I'm going to make bromine, and bromine goes around in pairs, so that's Br2, and I'm going to make that from bromide ions, Br minus. Well, Br minus, I've got to lose that minus charge. Br minus has a minus charge because it's gained an electron. It's got 8 electrons in its outer shell. And bromine, the atom, has 7 electrons in its outer shell. So it's got to lose an electron. So plus E minus, well, I need 2 bromide ions, and it's going to lose 2 electrons. Each bromide ion loses 1 electron to become a bromine atom. And so that's the equation there for 2 marks. The next part was an easy 3 marks for a balanced equation. It says aluminium reacts with chlorine to form aluminium chloride. Well, this is really quite basic. Aluminium metals always go around on their own, so aluminium is Al. Chlorine is a diatomic molecule, Cl2, so you've got to draw chlorine as Cl2, and then you've got to write the formula of aluminium chloride. Aluminium chloride, aluminium is in group 3, so Al, it's got a 3 plus charge. Chlorine is in group 7, so it's got a -1 charge. So the formula, using the crossover rule, the formula of aluminium chloride is AlCl3. Now that's got you 2 out of the 3 marks. You get 1 mark for the aluminium and the chlorine on the left hand side, 1 mark for getting the formula of aluminium chloride right. The problem then is that you have to balance it, and the 3rd mark was for balancing. Now you've got 3 chlorines on this side, on the right hand side, and 2 chlorines on the left hand side, so you need a common denominator of 6, and to give me 6 chlorines on each side I need 3 of those and 2 of those. If I've got 2 aluminium chlorides, then I'm going to need 2 aluminiums, and that will give you your 3 marks. The last part was really quite straightforward, part D. A solid ionic compound is dissolved in water to form a solution. Describe a simple experiment to show that charged particles are present in this solution. Well, when ionic compounds dissolve, the ions are free to move, and the easiest way to prove that it conducts electricity is to use electrodes. So take the solution and add 2 electrodes. that's 1 mark. So what I'm doing here is I'm using the solution for electrolysis, and if I can do electrolysis on it, then it's got charged particles that can move. So I add 2 electrodes for 1 mark, connect the electrodes to a battery or power supply. That's for your second mark, and then you need to show that there's a current flowing around the circuit, and you're going to do that and by either putting a bulb in the circuit or using an ammeter. So measure the current using an ammeter or bulb. And that's it, simple 3 marks. Question number 6 says the rate of reaction between magnesium ribbon and dilute hydrochloric acid at room temperature is investigated. The apparatus used is shown in figure 6. The volume of hydrogen gas given off was measured at regular intervals during the reaction, and a graph of the results of this experiment was plotted. It says, state a change that can be made to the apparatus in figure 6 to measure the volume of gas more accurately. This was a little bit tricky actually. You could use a thinner, taller measuring cylinder or a burette. So use a thinner, taller measuring or a burette. So a long, thin measuring cylinder, essentially a burette is. Or you could use a gas syringe. And a gas syringe is another method of collecting the gas that is more accurate than displacement of water. Now, over the page, part 3, I'm just going to draw this on here now. It says, draw the graph that you would get if the magnesium ribbon was replaced with the same mass of magnesium powder. Now, if you use powder as opposed to ribbon, the particle size is going to be smaller and the reaction rate is going to be quicker. Now, the key thing is the rate might be quicker, but the amount of hydrogen that you produce is the same because you've got the same mass. So in other words, you'll have a faster rate of reaction, but the extent of the reaction, how much reaction occurs, will be the same. So on your graph, what you will have is a faster rate of production, but it will finish in the same place. So that's what the graph would look like if you use magnesium powder as opposed to magnesium ribbon. Now part 2 says a tangent has been drawn to the line on the graph at figure 7. Calculate the rate of reaction at this point. Well, the rate of reaction is the gradient of the line, and the gradient of the line in centimetres cubed per second is, you work out by the change in y over the change in x. So it's dy over dx, the change in y over the change in x, and if you measure the change in y on your graph, you've got 43 minus 15 over 60 minus 0. So you've got a value of 28 over 60. That gives you a value equal to 0.47. So that gradient of that line is 0.47, and that is in centimetres cubed per second. So 0.47 there. We've done part 3. The line will be steeper but finish at the same place. And B, a balanced equation for the reaction is, and then it gives you the equation, and it says in another experiment 0.1 moles of hydrochloric acid were reacted with 0.1 grams of magnesium ribbon. Calculate the number of moles of magnesium in the 0.1 grams of sample. Well, moles equals grams over rams. In this case, the grams is 0.1. The ram of magnesium is 24. 0.1 divided by 24 equals 0.0042, or 4.2 times 10 to the minus 3 in standard form. Part 2, it says, in a further experiment, 0.5 moles of hydrochloric acid were mixed with 0.5 moles of magnesium. Use the equation to show that in this experiment the magnesium is in excess. Well, you didn't have to do any calculations for this. What it's saying, the balanced equation tells me that 1 mole of magnesium reacts with 2 moles of hydrochloric acid. So I've got Mg plus HCl. This is 1 mole reacts with 2 moles. And I get that from the equation. Now, what I've actually got is Mg plus HCl. I've got 0.5 moles of HCl. That means it's going to react with half as much HCl. So I would expect 0.25 moles of Mg. Well, I haven't got 0.5 moles. I've got 0.5 moles, twice as much, which implies that the magnesium is in twofold excess. Right, part C was the first of the 6-mark questions in this paper. It says, 2 substances A and B each form a colourless solution. If the solutions are mixed in a beaker, A and B react to form a coloured product. The rate of reaction between A and B can be investigated by placing the beaker containing the mixture on a cross on a piece of paper and timing how long it takes for enough coloured product to be produced to make the cross invisible when viewed from above through the solution. Now, this is an experiment that you did for a core practical. You measured the rate of a precipitation reaction, and it's an inverse relationship. The quicker that the cross disappears, the faster the rate of reaction. So the shorter the time, the faster the rate of reaction. And it then gives you a number of experiments. You've done 3 experiments where the concentration of A is varied, the temperature is varied, and you measure the time taken for the reaction to happen. Now, it says use the results of these experiments to explain in terms of the behaviour of the particles, the effect of changing the temperature and the effect of changing the concentration of A in solution on the rate of this reaction. Now you got 6 marks for this, and I split those 6 marks up into 3 separate areas. The first thing was explain what happens to the particles in the reaction when it happens, and that is collision theory. So state collision theory and why reactions happen. Then state the effect of changing the concentration for 2 marks. And then for another 2 marks, state the effect of changing the temperature. And that's how the 6 marks are divided up into the mark scheme. And we're going to have a look at each of those sections in turn. So the first thing that you need to include if you're answering a question about how the behaviour of particles affect reaction rate is you need to describe the theory of collision theory, and this is what this is. This is collision theory. And collision theory says that reactions occur when particles collide with enough energy, and that energy is the activation energy. So you had to say, first of all, that particles collide with greater than or equal to the activation energy for the reaction to happen. And many of you missed this first bit. You went straight into describing the results, and that's where you've lost your marks. And it says reaction rates are increased when the energy of collisions increased or the frequency of collisions is increased. So reactions go faster because particles heat each other with more energy or more often. So frequency collision or greater energy of collisions. The two factors in the reaction that have changed were temperature and concentration. And then we're going to go on to look at those two in detail once we know that reactions happen because particles collide with enough energy. So the next thing to do is to describe the effect of temperature. Effect of temperature on rate of reaction. So if we have a look at the results, we can see the difference between experiment 1 and experiment 2. We have doubled the temperature of the reaction, but the concentration has stayed the same. So if we're studying the effect of temperature on rate of reaction, we need to say that experiment 2 was carried out at twice the temperature, but the concentration was kept the same. Now, between those two reactions, if we increase the temperature, then the particles will move faster, they'll have higher kinetic energy. So there are more frequent collisions, but there are also more energetic collisions. So increasing the temperature has two effects. It means that the particles collide more often, and they also collide with more energy. So therefore you're going to have more collisions with the activation energy, and therefore your rate of reaction is going to go faster. Now, because of those two effects, because of the effect of more energetic collisions and more collisions, then you're going to have a large effect on the rate of reaction. And in fact, doubling the temperature has effect of quadrupling the rate of reaction because the time is decreased by a factor of 4. So in summary, experiment 2 goes 4 times as fast as experiment 1 when the temperature is doubled, because you get more energetic collisions, you get more frequent collisions, therefore you're going to have more particles with greater than the activation energy, and the reaction will go faster. So the last 2 marks were for saying the effect of concentration on rate of reaction, and here we're looking at the difference between experiment 2 and experiment 3, and we've kept the temperature the same, but what we've done is we've increased the concentration by a factor of 4, and that increases the rate of reaction. It decreases the time by a factor of 4, so it increases the rate of reaction by a factor of 4. Now, the reason for that is that as you increase the concentration, you get more particles in the same volume, therefore you're going to get more frequent collisions. It's just a single effect, more frequent collisions, so therefore you're going to have a greater number of collisions with energy greater than the activation energy, more frequent successful collisions, therefore you're going to have an increased rate of reaction. But it is actually just a linear relationship with concentration, that if you increase the concentration, if you double the concentration, you double the rate of reaction. You don't get that double whammy that you get with temperature. Now, you needed to say all of those things in a really well structured answer to get your full 6 marks.